Hi, this is Professor Jimenez, and today we will see the analog to digital converter, which is embedded in the PIC 16F1619. In my book on the PIC microcontroller notebook, volume 2, second edition, this one corresponds to lab practice number 4. And it might have a different number in other of my books or lab practices notebooks that I have. In this case, we will see this practice, and where we apply a voltage on analog input A and 1 on port A, that voltage will be applied using a trim potentiometer, a trim pot, which can be any value within 5K up to 100K. And the result of this voltage, which is converted to a digital reading, will be placed on port C. First, we will see it with 8 bits, because this is the most basic way to understand the A to D converter. Okay, to take a look at how the project or this practice looks, this is how it'll look. So you have the A to D converter right here, the PIC 16F1619, and we have a LED bar graph with 10 bits, but we can use 8 or 10. Each LED requires 180 ohm resistors in this case, but it can be from 120 up to 400 ohms. So every LED has a jumper to port C and 2 more bits, which might be in another port, and this is the trim pot. And the trim pot has power, has ground, but before going to power, in this case, it has a resistor, a series resistor to voltage. This is just to protect the potentiometer in case it reaches a value of 0 ohms, to avoid short circuits. Okay. Now we will see the PDF document regarding this practice, and so here we have the chapter 17.0 from the microchip data sheet, and notice this is a data sheet. Okay, so we will see the chapter 17, A to D converter. And this A to D converter allows conversion of analog input signals into a 10-bit binary representation of that signal. So this is the schematic, and notice that here we have the analog inputs from AN0, AN1 up to ANZ, and then every single one of these, it is selected using this multiplexer. This is an analog multiplexer. The selector channels, CHS, are from 0 through 4. So with these 5 bits, you can select any one of these, or you can select a ground. You can select an internal temperature indicator, which is embedded in the microcontroller, and we also have a DAC and digital to analog converter, which we can use as a reference, and a voltage regulator, okay, from another block which we can select. So these are external channels, and these are internal channel inputs. The temperature indicator allows you to measure the temperature in the chip. So That way you can determine if the chip is operating under normal temperature operation. And also, one of these inputs in the channel inputs, it is known as the positive reference voltage, and this can be selected with this code using these 2 bits. Okay, so those bits allow you to make this one a reference voltage. That way you can change the range of the sensor. So if you have a sensor that on any one of these inputs that works in a voltage range less than 5 volts, for example 0 to 1 volt, so you want to have the maximum resolution by selecting the positive reference voltage and putting an external reference equal to 1 volt. That way you will get the maximum resolution. And also by default VDD is selected, so your positive reference voltage, if these are zeros, you will have 5 volts right here, and that's your voltage, your positive voltage reference, which allows you to, as I said before, allows you to work in that range that you are selecting. The negative reference voltage is placed by default to ground. So notice that you can only work with sensors that work from 0 to the reference voltage, in that range from 0 to up to the positive reference voltage. And you really need to have another type of sensor where, for example, a sensor that provides the 0.5 volts to 3 volts, for example, and you want 0.5 volts to be equal to zeros in binary code. So you will need a CAS circuit, a signal conditional circuit, and that has to be external, made with external operational amplifiers or op-amps. The ADC converter requires a clock selection. So it has the clock can come from the crystal, from another clock source, and you can select it. So the clock allows you to select the conversion speed or the conversion time that it'll require to have a conversion ready. Every time you sample an input voltage, the voltage has to be converted into a 10-bit result, and it'll take a conversion time. Sometimes the standard is almost 5 microseconds conversion time. And every time you take a reading, the reading is stored as a 10-bit result, and you can select that result is stored in these 2 registers: analog to digital result low byte, or analog to digital result high byte. Okay, and those 2 registers, this is an 8-bit register and this is a 2-bit register. Okay, here you have a MOSFET transistor which switches the analog to digital to ground. That way you will turn on the A to D before doing a conversion. That's good to have, because if you want to save energy in battery operated applications, you have to turn it off and only turn it on when you need to take a measurement. And here we have another register, 2 bits, which in this register you have to write the go to start a conversion, and the bit will return to its initial value to indicate that the conversion is complete. So when the conversion is complete, you can read that bit, and then you are ready to read or use and control this and do other operations. Or you can wait 5 microseconds, but it is not convenient. It is more convenient just to determine when this bit changes. That way we know that the result is ready. Okay, there are other trigger selections, other ways to trigger sources with this trigger select to start a conversion, but this is a general schematic for the A to D converter. Also, the following things must be considered when you are configuring the A to D converter. You have to make sure the port configuration is correct, right here, and you have to select a channel, then make sure you have the voltage reference, the VRF positive. You have to select the conversion clock source, the interrupt control, and you might select the result formatting, so which is left justified or right justified. Right justified will be the most common for the, in our applications. Okay, and now you have to make a channel selection right here, and this channel selection, and you can have channels 0 to 11, and or these channels 0 to 7 only in this chip that we are using, this one, the temperature indicator or the DAC output or the FBR, or the voltage regulator. And the conversion clock, the source of the conversion clocks is software selected via the ADC bits, so we can have many options there. And these are the device frequency operation, and depending on the crystal, the oscillator crystal, we are working at 4 megahertz, so you select FOS over 4, so it'll take 1 microsecond to do this, to have this clock period on the ADC. Okay, and this is the format for the conversions is this. So you have let me clarify the light right here. Okay, you have the bit, the format justification of that bit. This bit is known as ADFM. So if that bit is equal to 0, your conversion will be this way. The least significant bit will be here, the let's say bit 0, bit 1, and you have a 10-bit ADC result. Okay, the least significant bit will be here. This is the second bit, and then the rest of the bits will be here. Notice that the most significant is there. This is not common, so the most common way we operate is using ADFM equal to 1. Okay, and because in this mode we have the least significant bit here and the most significant bit here when we are using 10 bits. But if we are using 8 bits, the LSB will be here and the MSB will be there in bit 7. So this will be our more common mode of operation. So notice that don't forget that ADFM must be equal to 1. That's the analog to digital format. Okay, and for the ADC operation, these are the steps. You have to clear the go down bit, set the interrupt flag, but we will use another way of operation for this practice. But before going into the code, I want to show you that the A to D conversion register, there are several registers. One of those is AD con 0, okay, or analog to digital control register 0. And the AD con 0 has 8 bits. Bit 7 is not implemented. So notice that here is the AD on. So this is how you turn on the analog to digital converter. This is how you start the conversion. To check every single bit here, I'm going to use this. To check every bit, you have to just scroll down the data sheet and you will see there the operation. In this case, you can see go done, or bit 0, AD on. So first you enable this bit, so you turn on the A to D converter. You wait a few milliseconds and then you can start selecting the channel. And how do you select the channels? They are right here in this register called channel selection 4 through 0. So there are 5 bits, and according to the bit steering or bit selection that you do here, notice that you have all these different selections. So you want to select channel 0, you will do this code 0, all zeros, channel 1, AN1, channel 2, 3, 4. So, and they correspond to its binary equivalent. Okay, and notice that 8 numbers, 8, 6, 5, or these are reserved, so there's no channel selection here. Okay, and for these codes, but from AN7 you jump to AN8. Okay, this is how you select channel 8, channel 9, channel 10, channel 11. Okay, and even though channel 11 looks like a number, yeah, that's 11 in binary. This is 10 in binary code. Okay, so this is how you first you turn on the A to D, and then you select the channel with these bits. Okay, and once you select the channel, you can start the conversion, but before starting the conversion we need to select the clock. Okay, and the internal clock, and we also have to select the ADFM bit, which we saw a moment ago. It is this one, the format, the analog to digital conversion format. And according to this bit, ADFM is right here, and this is bit 7. So we're going to make it equal to 1, because by default you can see here it is equal to 0, so we will make it a 1. So we will do the right justification. Okay, right justification, and then we select the clock source, so we can select it for like F over 4, or the clock supply from an internal RC oscillator is number 3. This is the most common for us, so let me make sure you can see it here on the screen. Yeah, so this is the most common. Okay, the clock source will be the internal oscillator, which is already there embedded in the PIC micro. Okay, and then we have the analog to digital positive reference voltage. Okay, so if it's going to be connected to a fixed voltage reference, or it's connected to external voltage reference, okay, or if it's going to be connected to VDD, this will be the most common for us in the first experiments, in this experiment. But if you are working with this in an instrumentation experiment, and your sensor requires an external voltage which is different, then you have to select 1, 0. Okay, there are also internal fixed reference voltages. You can select it with number 3, but in this case it'll go to VDD. So our range for the trim pot will be from 0 to 5 volts. Okay, there is another register called AdCon2, which is the trigger selector. It has the trigger selection. So in case you want to trigger the A to D converter with these other timers, clock sources, and or the capture and control modes for coming from the PWM, we won't do it that way. And the ADC results will be in ADRSH. So right here, there will be your 2 bits. Notice here, when ADFM is equal to 0, this is what happens. And when ADFM is equal to 0, this is what happens in every address L. But when ADFM is equal to 1, which is our case right here, when it is equal to 1, so we will have in this part of the register right there, we will have the most significant bits, and on this register address L, okay, right there we will have the bit 0 through bit 7, which is the format that I explained a moment ago at the beginning of this lecture, indicating that this will be the one we'll be using, okay, when ADFM is equal to 1. That's our case. Very good. So now we have to go back, because remember I said that when we are working with this A to D converter, and we have to turn on the A to D converter. There, we turn it on. We select the channels. We select the clock, as I indicated 2 minutes ago, and then we start a conversion with a go down bit. Okay, so when and you want to read about that bit, it is here. So it says this. Let me mark it, because this is very, very important. Okay, so is the ADC conversion status bit. If it is equal to 1, ADC conversion cycle is in progress. So you have to set this bit, and then you wait. You can read it and wait for the bit to go low. So once the bit goes low to 0, the ADC conversion is not in progress, it's ready. So the conversion has been completed. The good thing is this bit is automatically cleared by hardware when the ADC conversion has completed. So that's the way to determine when a conversion is ready. Okay. So this lesson is complete with respect to the hardware things, the hardware architecture, we can say, about the A to D converter. In my next lesson, I will use it to explain how we can use a software to take a voltage reading and transfer that voltage reading into this from ADRSH and L to port C, so that we can see the reading. Okay, so we're almost we have almost completed 25 minutes, and so notice this is the chapter we were covering today, chapter 17 from the data sheet, and then we will go into the code to write a short code to make the conversion work and get a voltage reading. Okay, thank you very much.